Okay, so I'm gonna share screen. Let's put it this one. Yeah, you're typically will have like about 7 to 10 days to do something like this. Yeah, with 3 or 4%, maybe 3%. So we have nine or 10 people here. So around 3 4%. Yeah. Right. So I'm gonna open this one, and also I'm gonna open the PowerPoint. So we can have an idea which one. Okay, let's have a look on the Fenske method. Yeah, which one? Which part? Sorry, which part? You don't understand? Which one? Maybe let's put here, or maybe it's better if also put the report. Yeah, let's put the report as well. Yeah, this one. Okay, let's check the oops. Oops. Which is okay. So in the problem, they have 1, 2, 3, 4 components. Okay, and you know the feed, right? And this is the composition. Okay, and then we know the information about 93.75% goes into the yeah should be keluar ya it should be in the distillate, this one. And also we know the feed of the feed of the feed temperature, yeah, 100 degrees Celsius. And we also know the pressure. Okay, and also we know the state of the phase of the top product and also bottom product as a saturated liquid. Okay, so based on that one, let's open in here. Oops, maybe let's put it in the shortcut method there. So okay, so here this one is from the uh, this one is from the problems. Yeah, so we put 0.02%, 32%, 45%, and 22.8%. Okay, up to here, is it do you understand up to over here?
Yes, Bu.
Yeah, okay, right. And then based on this one, uh okay, you also, and then after that you need to calculate which one goes into the distillate by multiplying about in this case about 93.75% multiply with the G3, where is it, with the feed. Yeah, so, okay, sorry. And then after that you multiply it, the components with the feed. Yeah, with the where's the feed, nah, this one. Yeah, feed masuk. Okay, so then you understand the composition, you know. Yeah, this one, the blue one is your calculation, so that is right. Yeah, the blue one is the calculation, so that's right. And then you know the component, you know the feed, and then you multiply it with the composition with the feed, and then you get the feed for each component. After this, right? Okay. Now, based on the problems here, 93.75% of propane and also 2.25% of normal butanes will go out as the distillate. Okay, so we just need to calculate based from the feed. We calculate this one. Yeah, 93.75% multiply with the G31 is the feed. Yeah, there. And this one also about 2.2%. Is it should be G1, yeah? That one. Okay, G32. Okay, so about 2.25% of the in the feed goes to this one there. So this one is the one that we know. Yeah, that we know about the feed. The one that we know from the distillate. We know 150 from the C3. We know also NC4 in the distillate. Also this one based on the problems. Okay, we don't know which one goes into how many C2 goes to the distillate. We don't know that one. Okay, but we assume, yeah, so this is the red one is the assumption. We assume if, for example, yeah, 160 from 160 150 goes into the top one, so I would guess that for the one that is more volatile, because C2 is more volatile, maybe all of them goes to the distillate. Okay, karena 160, 150-nya ke distilat, banyak banget yang masuk ke distilat, ya, maka mereka berasumsi kalau dia punya satu yang paling lebih ringan daripada 150, asumsinya berarti semuanya harus nguap. Yeah, that how to make your assumption. But for example, but I want to make assumption maybe only half of them goes to distillate. Yeah, maybe you can do it as well, because this is an iteration, ya, nilai tebakan, a guessing value. Okay, and this one we also don't know. Yeah, the how many N-pentane goes into the bottom, we also didn't know. Okay, so we have to guess. Okay, so here in the feed we have 114 kilomole, yeah, 1 kilomole there. So, but we don't know, so you may want to guess, or maybe only little here from maybe 2.25 only 5. So maybe, yeah, this is should be little, because NC5 is the very quite heavy, so it should go majorly in the bottom. So this is a guessing. Okay, up to here, any questions? Hello.
Clear, Bu.
Clear? Okay. Yeah. So with that, you subtract the bottom, yeah, from the feed. This one also you subtract the bottom, yeah, from the feed, and then you got the bottom. You also got the bottom here from the feed to the distillate. Yes, basically that one there. So once you know the mass balance of each in the feed, in the distillate, and the bottom, then you can calculate the component. So the component is based on the amount of a distillate divided by the total. Okay, and also the component of the bottom is also the distillate in the bottom divided by the total. So I think the best way to learn this one is to have an assignment by yourself. Okay, but because you will also have assignment on the tri-column design. And usually in last year we have also assignment on multi-component design. So but actually this is the same, both of them is the same. And then from the questionnaire, some of you are the students also complain why there is too much work for distillation for separation processes. So I asked the team teaching to let's have one assignment on multi-component the multi-component distillation on the tri-column design. So tomorrow or maybe next week, I'm gonna explain about the tri-column design, so about the equipment. So we're gonna do equipment design, like how many trays do we need, what type of the trays, how long is the height of the tray, okay, how to design a good distillation tower like that. And also I'm gonna explain about the basic of computer style, or we call it rigorous method. Looks like I'm gonna explain rigorous method now, but looks like the regular class is still doing the exact method, so we still have time. It's about basic, but rigorous method is just to have a knowledge, and I'm gonna explain to you about HISIS as well. So you can later you can try by yourself using HISIS to compare your calculation like this, the manually using Excel and also using HISIS. So with that one you have a very deep understanding about how to design a multi-component distillation from the manually like this, from the Excel, and also then from the HISIS you can compare it and then you can validate it, and after that the tri-column design. Okay, so and then that will be evaluated in the oral exam, a group exam, but the problem, or sorry, the penilaian, the evaluation is for everyone, so every students will have a different evaluation, of course. Kayak pembicaraan, looks like pembicaraan lab, right? Okay, so okay, this one's done. So here, while this is assumption, so it's not might be right, and then also who's this one, Widi and the your kakak tingkat have done this one by one, and also they does a very good job because they have a nice Excel, like this one. So if you know how to make it presentable Excel, please do so, with centered, for example, with the bold, and then so your Excel should be able to be read by any other person, any other engineers there. Okay, and with that, so the mass balance and also the component balance is done, and the next step is we have to find out the K value. Why we need to find the K value? Anyone? Dama, why we have to find the K value for each component, each state? Fatia? Hello? No idea? Alisa? Why we have to find the K value?
I think, if I'm not mistaken, K is related to thermodynamic data, Miss.
Yeah, that's right. Yeah, that's very correct. So K is actually Y divided by X. So instead of we are using graph, so we have to write the thermodynamic data, So like why we have to find the K? Because we want to know the correlation at this point. What is the correlation of the Y? So why divided by x, yeah. So in any cases here, in for example, in the distillate, in the bottom, for example, if you know the x and then you know the k, you can predict the y. Okay, so that's why we have to do the calculation of k. How to get the k? How to get the k? Fatia, have you explored how to get the k? We go back to the regression, this one. Yeah, so what they've done is to open again this no, not this one. They open this one. We will give you the nicer one, yeah, because mana sih nih, this one. Oh, not this one. The first one. Yeah. Okay, they use the k value. Okay, the k value, and then put for example one typical typical pressure, or maybe the pressure is 1/8 okay, for example 1/850 based on this one there, and then they make several temperature, so one for example, and then they add it again. What else? For example, the second one. So they do it for several temperature, maybe 3 or 4, yeah, how many that one, and they read the scales. Okay, they read the scale for ethane, for propylene, for propane, for isobutane, and also for n-butane, and also for isopentane. Okay, so they try that one, read that one, and then they have this value. Okay, the question is, can we have an error in the reading? Of course, yeah, we can have error in the reading, because this is a very small numbers, yeah, and then also the k value is very small as well. So this one is from the yeah, of course there would be some errors, but that's fine, because we really want to learn how to do it manually. Okay, and they put a graph there. Okay, for ethane, for propane, for butane and n-pentane, and then they make a regression, and then this is nice regression because 0.99, yeah, for the linear, so we can assume that it is linear with these equations. Okay, so with that, then they can calculate how many, for example, this one. Okay, so based on the parameter. So yeah, so this based on the parameter. Okay. Now, what is the next step? So once they know that the k, if we go back into the Fenske method, If we go back to the Fenske method, okay, we need to find log alpha average. Yeah, we need to find log alpha average. So this is how they done. They calculate the first is the DLK, yeah, based from the, of course, the light key over there. BAHK is also the bottom, the bottom, yeah, of the light of the heavy key and the light key, and then they calculate the alpha LK average. What is alpha means? What is alpha?
Relative volatility, Bu.
How to get that?
The ratio between the K of F over the heavy component.
Yeah. Okay. So if you are asked alpha average is actually the alpha light key. So your relative volatility would be K light key divided by KHK. Okay. If you are asked alpha I, the relative volatility of I component is also KI divided by KHK. Okay. So if I want to ask, what is the relative volatility for heavy key? So if I ask a relative volatility for heavy key would be equal to KHK divided by KHK, which is equal to 1. Okay, so when you do calculation, think again, think a little bit about the K value. So usually the K value should be more than 1 because it's a light key divided by, for this case, yeah, because the K, see, the more volatile a component is, the K value is more higher. Okay, the more least volatile of a component, the K value should be less than 1. So K value less than 1, so there would be more X than Y. Yeah, so the Y is small, so which is the would be better to be in the liquid phase. Okay, but if you have a very high K, that means your Y would be much higher than the X. Okay, so that would be more volatile. Okay, based on the Fenske method, you have to calculate the log alpha average. So then you calculate it, this is the alpha average, and based on the square root of alpha LK in the distillate and also the alpha LK of the product. And then they have 7 on 6.8 and then round it into 7. Okay, okay, so this one, and then after that, okay, then if you look at here, okay, if you look at here, okay, so then you have the NM is that one 7, yeah, based on here, or 6.87, and then you run it up into 7. Okay, and we have a little bit of problem here because we still use this one as the iteration. Yeah, it's still a guessing. So what can you do? Actually, they use a two iteration. Yeah, yeah, because it's only 3 iteration. So what they do is actually, okay, because they know the NM, yeah, which is in this case is sorry, let's put it here, yeah, because they know 6.87, yeah, based on this one, based that one, the NM, and also they also can calculate alpha I average, they can also calculate the alpha I average. And after that, so this one is, so let's check with this one, yeah. So we know the NM, yeah. We also know the alpha I average because it is alpha K I divided by KHK. We also know the D of the HK. Okay, so then we can find DI and BI. Okay, this one there. So this is how they open it. Okay, this is how they try to see. This is so they find the new DI over BI based on the calculation. This one, yeah, based on that one there from the NM. Okay, they also can find the D2 divided by B2. They also can find the D3 divided by D3. Sorry, D4 divided by B4. So they can have they can know the exact value of this and this. Up to here, any question? Is it clear enough? Hello?
It's clear, ma'am.
Yeah, okay, thank you. Okay, so now, so because we know the I and BI, we also know the F, yeah. F is FI, the feed, yeah, is also, we know the feed, so then they can solve the equation, and then they get the BI and also the DI. So apparently the real actually, yeah, while we have an assumption this is 1 and this 0, so it's actually quite right, 1 and 0. Okay, and if we assume this is 1, for example, in the bottom, the real actually is not 1 mole, 1 mole, but only very little, which is 0.006. Okay, so now this one is your composition. Okay, so this is your real mass balance, and this is your real composition. So then this one is the composition for the bottom, and this is also composition of the distillate. Okay, so that is the Fenska. Yeah, it takes a long time, of course, but that's why you can't do it only one person, so there should be of course a group, yeah, a group assignments, and because you're doing it remotely, you cannot go to someone's kosan, yeah, and then do it together, yeah, for a few days, for example. So that's why it's gonna be hard or something, yeah. But in the previous years, we never do this one. We never explained all the detail of the Excel, yeah. All the Excel is up to you, yeah. It's up to every group to determine their Excel, because how engineers do, we never so we have the way of every engineer do, yeah. So as long as the Excel is we can read it, it is easy to understand, we can bisa mengikuti, ya, we can follow the Excel, that's fine, yeah. Okay, now so we know the minimum stage. The second one is the VF, yeah, based on the Underwood. Okay, on the Underwood, okay, so this is the Underwood. Okay, so this is a sigma. Where is? So this one is the sigma I into C. So if you have 4 components, then you have 4 I's, and then this one, and then a summation of that one. So you know the alpha of I, yeah, for in the feed. You have also the Fi, which is the mass of the feed, each component in the feed. You also have alpha, this one there, yeah, alpha I, the relative volatility, and minus the Cu that which is we want to find. But before that, we also need to find the VF, which is the vapor molar rate of feed. Yeah, because in the problem, they didn't say the state of the feed. Yeah, they didn't say the state of the feed or the phase of the feed. Is it saturated vapor? Is it a saturated liquid? Is it subcooled liquid? Is it superheated vapor? There's nothing that is mentioned there. So we have to calculate the phase of this feed by using flash calculation. Okay, and this is the flash calculation. Okay, untuk menghitung menggunakan persamaan under root 1, diperlukan data VF atau fraksi umpan yang berada dalam bentuk uap. Oleh karena itu, perlu dilakukan perhitungan menggunakan flash calculation. Okay, you maybe have learned in the thermodynamics before that in order to find the vapor, yeah, or fraksi umpan, the vapor fraction, this is the formula. So Z is the composition, yeah, multiply with the Ki, the K of the components, divide by 1 plus the vapor fraction, multiply with Ki with minus 1. It should be equal to Yi, okay? And they expanded for component 1, component 2, component 3, component 4, and then you will find there are 1, 2, 3, 4, yeah, the values. And then so you have to use Goldthik, okay? Remember Goldthik, the Goldthik from Excel. Forgot which one. So the yeah, and then find it in the Excel how to get the Goldthik as using sulfur. Yeah, okay. For example, set objective by changing something, yeah, and then you check the like a Goldthik, and then you can solve the sulfur parameters. Okay, and they did that, and then they found that the vapor fraction is the 0.4639. Okay, that is from the Goldthik. Okay, now once we know that one, the vapor fraction, then we can use the Underwood one. Okay, and you know the sigma I, and also with the feed, and also you know the the alpha I, not the sigma, yeah, the alpha I and minus C that we want to get one. Again, we have a nonlinear equation here with four for that one there, and we using tebakan, yeah, using the guess would be between 1 and alpha LK. So alpha LK, or the relative volatility of light key, is about 2 point something. So then they got this one, 2.3198. Okay, so nilai yang didapat adalah valid karena harga C berada dalam rentang antara 1 dan LK, yeah, which is 2,3 something. Okay, up to here, any question?
Ibu,
Yeah.
what should we do if the value is not within the range?
Nah, you have to find another tebakan. So because when we calculate this one there, you have to use the guessing value, yeah. So you I think you may need to guess between 1 and 2.3. So maybe guess around half of it, yeah. 1.6 or 1.7. Maybe the solver will tell you that one there. Okay. Because if you use a different guessing tebakan yang berbeda, you may have a different value. Okay, the principle of this one is like a Newton-Raphson. Do you remember Newton-Raphson in the process computation? Do you remember Newton-Raphson? In the Newton-Raphson, if you have a function, for example, like this, yeah, you have 1, 2, 3, 4 value. All of the will make this equal to 0, yeah, because in this is in the function. Okay, what make difference is how you put the guessing initial tebakan, yeah, the initial iteration. If you start with this one there, for example, they will find up to here and then go to that and then convergent and then goes to that one there. If you use guessing tebakan from here based on that one, and then for example maybe you can get to here and then it convergent goes to that one. Okay, so it's really based on the, because here you have four variable for C over here, we will end up with four different persamaan, ya, kayak persamaan quadrat, for example, ya, the squared equation, but then you need to find use the guessing tebakan 1 minus C minus 2.323. Okay, is it answering your question? But if in the real assignment you have a problem with this one, we have to have a look again at the Excel. Yeah. Okay. Right. Now the next one is the Underwood 2, which is now much easier because we just need to put all the value there, and then you got the value there, then you get the R and then R 4.1. Okay, and then they use correction of the Gilliland. So especially if you want to use the correlation is fine, but these people here use a correlation based on the book. That's also fine because this is actually the one that explain about this one. Yeah, so both of them is fine. So then you can find the number of stages. For example, for 14.22, and then you round it up into 15. Okay, if you want to use a Kirkbride, you may want to get the ratio of the NA and also NB, and then you have two equation, and then you have two variables, and then you can get which one goes into the NB and also which one goes into the NA. Yeah, it's fine. Okay, so this tell you from the shortcut method, you got the number of stages, you got the reflux ratio, you get the which one goes into the top, which one goes into the bottom, and this would be the input for the exact. Okay, up to here, do you think do you think it's better if we give you the assignment from now and then have more time to do it, or what do you think?
When is it due, Bu?
Nah, that's the things. Let's open it and okay. I think it's better if we maybe start it, yeah, or maybe have 2 weeks or more, yeah. So we're in the week 7 now, so we should be think about so tomorrow I should I will check with the regular classes. So tomorrow maybe I will explain about the rigorous method, and then I may want to explain about HISIS as well, so you can have a heads up to try the HISIS. You can ask Pak Indra, yeah, in that TU to ask you how to install the HiSys. So because we have the institutional HiSys, me by myself also asked Pak Indra to install the HiSys in my laptop, yeah, in the Windows laptop. So you please ask to Pak Indra, or I don't know who should ask, yeah. Yeah, I think Pak Indra there. And then after that, in the week 8, which is next week, we will design the tray column. So I'm gonna explain the type of the column, the design standard, yeah. And then here you actually will have the tugas perancangan. Yeah, week 8 then. Usually the one week isn't enough, of course. I think we will move to the absorption in the week 9, and then the evaluation of this one will be held around week 10 or week 11 outside the class. Okay, it's gonna be outside the class, because you will have 1 hour with me, or maybe with others. Looks like I'm interested to check with the regular classes as well, and other lecturer can check these classes maybe for the oral exam. This is for the multi-component distillation and the tri-column design. So that's why usually there are 2 different assignments. First is the group assignment for the multi-component. The second one is the tri-column, but it contains the multi-component distillation as well. So let's just not do this one, but then goes to the perancangan. I will check with Bu Grace and also the team teaching where should we start to put the perancangan. But actually, if we for example put it in the week 8, which is next week, then the time would be around, so next week is 15th of October. You have about 2 weeks to do that. So around maybe 29th of October is the start of your perancangan, yeah, oral exam. And then yeah, that's to explain. Okay, or do you want to have the problem tomorrow, or which one do you think? Which one is better?
I think it's better to have it earlier, Bu.
Yeah. So you can try and have a look, yeah. Right. I'll discuss with the team teaching if we think that, because now we're thinking about we're learning the Excel as well. At least for the problem, you can have a heads up to do the multi-component distillation first, yeah, and after that then you can focus on the tray column. Okay, thanks for your feedback. All right, the next steps is the exact and the enriching. Okay, so this one, so these all the one that we get from the shortcut, yeah. We know the minimum stages, we know the minimum reflux ratio, we know the reflux ratio, we know the N, or the jumlah tahap operasi, the top stage and also the bottom stage as well. Okay, and also this one, yeah, to get the distillate and the bottom, how to get one. This one also very important, yeah. So let's have a look on this one, the T. Okay, so okay, so in the distillate, what is the in the distillate, what is the phase? What is the phase of the distillate? Is it saturated liquid or saturated vapor from the problem? Looks like it's a saturated liquid, yeah? Okay, because it is saturated liquid, so we have to find the T bubble. Yeah, So we have to find the T bubble, and then the T bubble is actually based on the, so you want to find the let's check it here. Yeah, so you want to have a guess to find the T bubble if you have 4 components there. Okay, so in the T bubble, it's actually the P total. The total pressure should be the composition of 1, X1, multiply with the Pi saturated, and then also plus composition 2 multiply with the P2 saturated, plus composition 3 multiply with P3 saturated, plus composition 4 multiply with the P saturated. You have each component from the distillate component after the Fenske method, because you have you know the composition there. Okay, the bubble of the distillate, and then you can get the and then you get the temperature. So we want to find the T, ya, dicari nilai T tebakan yang menghasilkan galat P total dengan P operasi menjadi bernilai minimal, ya. So they want to find a very small this one there, ya. Kita cari galat minimal, see. So you want to find tekanan operasi minus tekanan totalnya should be have a very low minimal, and then you do it by using Goldfish, yeah. So for example, from the data there, using sulfur, for example, set the objective. For example, this one, yeah, we wanted the galat is a minimum, for example, by changing the temperature of the tebakan. Okay, and then let's solve it. Okay, so yeah, because it should be in that one there, yeah. So oops. Oh, sorry. Let's just, oops. Let's, oh, not this one. Okay, yeah, 55 point something, yeah. Yeah, that one. Okay, try that one. So because the Pi saturated is a function of the Antoine and also the temperature tebakan, yeah, and also this one also the P2 also a function of Antoine, that one there. Okay, and for also with the similar one with the bottom, we also calculate at this pressure, and then we know also the composition of each components. We calculate the P total. That is have a very low delta or galat, yeah, with the pressure. Okay, jadi cari nilai tebakan yang menghasilkan galat total dengan P operasi sehingga bernilai 0 dengan menggunakan Goldfish, ya, dengan menggunakan Goldfish. Okay, so once you get that one, then you can put the distillate and also the bottom, yeah, based from your calculation. Okay, so here we have distillate and the bottom, and we have 15 stages. So we have the delta of each temperature. Yeah, the delta of each temperature is actually the delta, the temperature bottom minus temperature of distillate divide the N. Okay, so we assume that from the top to the bottom, the temperature will increase around 4.37. Okay, that's how we define the temperature. Okay, and after that we still have 7 minutes left, so I'm just gonna explain the first stage. Okay, and then here in the enriching, we know the operating line. Also we know the garis operasi atas, yeah, operating line, and also we know the checking. So first, the one that we know is the XD, yeah. Okay. Okay, you know the XD, and also this one there, and this XD will act also as the XY, yeah, XI 0. Because it is full condenser, so the composition would be similar with Y1. Okay, see, that's why in here the composition of Y1 is actually all the same. Yeah, there. Okay, so now once you know the Y1, this is based on the, okay, XD, we know the X0 there. You know the also the X0, yeah, over there. Sorry, okay, yeah. And then from the Y1, we want to find this one. Okay, we can get the Y1 from the equation of this one. R divided by R plus 1 multiply with the X I n minus 1, which is X0, okay, plus XD, this one, divided by R plus 1, and then we got the Y. Okay, and for the correlation of equilibrium, we use the K value. Yeah, the K value at temperature of the operating, yeah, the operasi. Okay, now and after that, okay, and after that, we have the Ki, and then we can calculate also the sigma, the alpha I, which is the relative volatility, and we can calculate the Yi divided by sigma I, divided by alpha I. Okay, and with that we can find the Xi, that one there. Okay, so this one is actually because here, because Xi, the new Xi equal to Yi divided by sigma I divided by the summation of Yi divided by sigma I. Why I should always say sigma, yeah, alpha I. Okay, so we can go back into here, just a very little, to the PPT. Oops. This is the criteria to get, this is the criteria to get the Xi. Yeah, so this one is the criteria to get the Xi. So the Xi is Yi divided by alpha I, this one, Yi divided by alpha I divided by the summation of them, and then we get the X hasil calculation, yeah, from the calculation result. We don't know if the X of the calculation result is good or not, so we calculate the YHK divided by XHK, this one. Check if this one is equal to K value of to the K value there, yeah, K value of the heavy key, yeah. If it is checking, if it is right, so then your tray is fine. But if it is not right, then you have to use your new KHK to find the new temperature, yeah, to find the new temperature. if in this one, yeah, this is the that would be find the new temperature over here. Okay, so sometimes yeah, you do this one with Golfik, yeah, tebakan. It can be 2 or 3 iteration, but we use so from the guessing temperature 55.7, so the real one that have a small galat, yeah, between the KHK and the calculated, maybe you can use the Golfik to find the temperature the operation. Okay, so even we guess that the temperature is 55, it can be some yeah, for example, it can be a difference. Okay, so you do it for every stages, so it can be quite long time to do that until you satisfied one of the checking to check that this is the feed yeah, the feed stage. Okay, so just in summary, just before you change into system utilitas, later you will have the composition of the fraction and also the temperature. So later you can have a temperature profile in each stages, and also the composition profile in each stages. All right, we should continue tomorrow. So thank you everyone for listening. And then if you want me to explain more about the exact method, we can do it tomorrow, or we can move on to the next topics. Okay, thank you very much everyone, and then I'll see you tomorrow.
Thank you, Miss.
Yeah, okay.
Thank you,
Thank you,
Bu.
Bu.
Thank you, Bu.